Hello, this video is still about demonstrating how to do several hypothesis tests for categorical data. So we're going to use somewhat real data set. First, let's read in the Framingham 1000 data set. So this is what it looked like. Worked on this data set before, so it's a part of the Framingham study data. First, let's see, if we want to investigate the research question, is CVD associated with higher risk of death or mortality? So what we can do is we can get the data for the CVD and then the data for death. Then if we create a 2x2 table, it looks like that. And if we want to do a chi-square test to test if for CVD and death are associated, remember in the demo using synthetic data, we created a table, put it into an object, and then feed that object into the function chi-square.test. So here we can do it in one step. Chi-square.test table xy. It gave us this result. But we can also have a shortcut. So we're doing a data analysis for real data set now. We don't even need the table function. We just say chi-square.test xy. It gave us the same result. And so in this case, the p-value is very, very small. So we reject the null hypothesis, and it looks like there's a statistically significant association between CVD and death. And this is well known, right? Cardiovascular disease is the number one killer in the United States. Okay. Next one, we want to demonstrate Fisher's exact test. It's a bit difficult because we have a large sample size, 1,000. So what I did is a little bit cheating. So I just get the first 15 rows of data. So DF2 is the first 15 rows of DF. And then I get the CVD, get the death variable, create the table. And then look at it's a table with small cell counts there. Okay. So we can, first let's try use the chi-square test. And you will see this warning message telling you chi-square approximation may be incorrect. Okay, so if you remember the mathematics behind the chi-square test, you know it's based on approximation. And in order for that approximation to be more accurate, more reliable, you have to have sufficiently large sample size. Okay, and if your data doesn't meet that assumption, then you get the unreliable result. And R will give you this warning message telling you, the chi-square test here may not be reliable. Okay, so then we can use the Fisher's test in this case, and you can see it give us the name Fisher's exact test for count data and data x and y. P-value is 0.25, alternative hypothesis, and the point estimate for the odds ratio, and the 95% confidence interval for the odds ratio. Okay, so in this case, the odds ratio is pretty huge, but unfortunately, it's not statistically significant. Okay. All right, the next one is the more complicated Mantel-Haenszel test, since this test is really for checking confounding, so let's say, okay, we think age may be a confounder of, CVD to death. Okay, actually, age is a confounder for everything. They say epidemiologists always stratifying on gender and the controlling for age. Okay. So in order to use this Mantel-Haenszel test, let's take a look at these documentation for Mantel-Haenszel chi-square test for counted data. And you can see to use that test, one way you can just use the X to arrange a three-dimensional contents table into an array, which we did in the example using synthetic data. But another way is you can have X, Y, and Z, where X and Y are exposure and disease, Z is the stratification variable. You can also use that. So here, let's do X to be the CVD, Y is the death, and since the original age variable is a continuous variable, so here I use the cut function to categorize it into several categories. The break points are 39, 50, 60, 70, 75. Okay. So if you want to see a frequency distribution for this categorical variable age category, you can see less than 50, between 50 and 60, 60 and 70, and above 70. Okay. So you got 4 groups. And you can put that age categorical variable into Z, and you simply call the function Mantel-Haenszel Test XYZ. Okay. So this gives you the name, variables, and the chi-square test degree of freedom, and the p-value. In this case, p-values are very small. We have to reject the null hypothesis. So there is potentially some confounding effect from age. And then you have also the estimate for the common odds ratio. Of course, in this case, it doesn't mean much because the odds ratio varies across all the stratum. Okay. But it computed anyway, and it gave you the 95% confidence interval for it. Okay. All right, next one is the McNemar's test, and you know this is for paired data. So we have to find the paired data in the data set, and I look at it. There's some visit 1, visit 2, and visit 3. So those are the data collected at different visits from the same patients. So they are paired. So here I'm just using the visit 1 and visit 2. I pick an outcome called current smoking. Okay, so I get the before to capture the current smoke 1, and after is the current smoke 2. So let's take a look at the table. And you can calculate the rate of current smoking at visit 1, that's 51%, and this rate drops to 45% at visit 2. Okay, and of course you can get the before and after, the contingency table. So this is a 2x2 table. It looks similar to the 2x2 table for chi-square or Fisher's exact test, but here it's very different because data are paired. Okay. So the off-diagonal counts 33, 68, those are counts that matters to the McNemar's test. They're discordant pairs. The counts on the diagonal line, like 420 and 374, those are counts that doesn't matter for the McNemar's test. Okay, those are accordant pairs. Okay. All right, so we can also say put this before and after into a data frame, and you know, this would be looking like this. So just keep in mind that each row are a paired data point from the same person. Okay, so we can do a hypothesis test using the McNemar test. The null hypothesis would be was there a no, not a question. There was no difference in the current smoking rates at visit 1 and visit 2. Okay, so here we can just use the McNemar dot test, the before and after, and this gives us these outputs. And here the p-value is rather small, so there was a significant statistic difference in the current smoking rate, and this partially due to the large sample size, and based on the point estimate, One is 51% at weighted 1, the other is 45% at weighted 2. So we can even say there was a significant reduction in current smoking rate over time. All right, thank you for watching. Hope this is helpful.